Hi everyone, welcome to lesson 3 of transformations. Today we're just going to combine the previous two lessons, lessons 1 and 2. Lesson 1, which was about translations, and lesson 2, which is about reflections and stretches. We're going to combine it all into one big lesson, into lesson 3. But before we do that, we're going to get going on an opener question here. Here we go. If we have function f of x equals x squared, if this is our function, which one of these options, A, B, C, D, will result in an identical graph? So first things first, you need to know a x squared graph is a quadratic. So it's going to look like a U shape opening up. And so basically we want the same thing opening up, or we want the exact same graph. Let's talk about all of these guys here. In option A, if you have a negative here, this is a reflection. The question is, where is it being reflected? This one here is a reflection on your x-axis. So you'd be reflecting it over your x-axis. Here, this graph would end up with a parabola going down. This is not the same as the original. We definitely don't want this one. In option B, what do we have here? In option B, we have another reflection. This is a reflection over your y-axis. So if I took my x squared and I reflected it over my y-axis, it ends up being the same thing. Here, this should be our answer. Let's take a look at the other two just to double check though. Here in C, we have a double reflection. So what do we have? So we have a reflection over the x and then a reflection over the y-axis. So in this case here, if you had your original going up, reflection over the x would make it going down, and then reflection over the y would still make it go down. So it's definitely not C. And last but not least, for this graph here, f of x plus 1 means that we had a vertical translation. You're going 1 unit up. So that means that there would have been a slight gap on the bottom here where the vertex was compared to 0, 0, where the original vertex was. So it's not the same. So again, B should have been our answer here. The equation here that's in the box, this equation here is going to be the exact same equation that's on your formula sheet for your Math 30-1 diploma. This is the equation for transformation. You have all four variables on here and they're all in the correct order. So again, just as a quick refresher, you have A, which is a vertical stretch. You have B, which is your horizontal stretch. And a reminder that with horizontal stretch, once you pull your B value out of the equation to go into mapping, remember that has to be a reciprocal if you put this into mapping. Or if you put this into a descriptor sentence, it has to be the reciprocal. You have H and you also have K. And of course, H here is your horizontal translation. And again, when you pull this out of the equation, when you go into mapping, it's going to be the opposite of whatever sign you see here. So if I have a negative H here, it's really positive out here. So H here is your horizontal translation. And of course, we have K, which is our vertical translation. And so again, anything with horizontal stretches, horizontal translations, reminder, there's something a bit special that you have to do with those two. Here, a quick note says the order we always want to use is reflections, stretches, translations, RST, in this order. So whenever you have a graph, you want to deal with all your reflections first, stretches second, and finally deal with your two translations last. You want to do this in this order just so that you can graph it or you can map it, and it's going to make your life a bit easier. In the very first example here, we have mapping a transformed function. So what do we have? We have f of x, and we're trying to obtain this new equation here. Consider this as either g of x, if you want to call it, or basically it's just a transformed version of f of x. So let's write down the transformations that we see. I always work left to right. So the very first one I see is this number 2. If I see a number 2 there, that's on the outside of the function. That's a vertical stretch by a factor of 2. And I have a 3 here, and it's within the function, so I have a horizontal stretch by a factor of, and a reminder, anything horizontal, think you got to do something special or extra. It's going to be 1/3. We're going to take the reciprocal of that 3. So in terms of mapping x comma y, original is going to have the following happen to it. Well, Horizontal only affects our x value, so we have 1/3 x, comma, and vertical stretch only affects our y, so we have 2y. Close bracket, and that's going to be our new mapping. Over here, let's take a look at this equation here. I got y equals f of 2x plus 6. Perfect. So in this example here, the very first thing I notice is I don't have a b value by itself. It's b combined with x here already. So what does that mean? We got to do something extra. We got to factor. So I'm going to write a big note here. We're going to need to factor on this one because you always want that b value by itself. So I'm going to factor out a 2 from this equation. And so it's going to look something like this. 2, and I'm going to factor it out. So I got 2 times x gets me back to 2x. Then 2 times what would get me back to 6? That'd be positive 3. Here, now I have a dedicated b value and a dedicated h value. So my b value is a horizontal stretch by a factor of, and again, if it's a horizontal stretch, we've got to do something special. We're going to take the reciprocal of it by a factor of 1/2. I have a horizontal translation as well, and it's going to be this positive 3 here, so that means horizontal translation 3 units left. And so for my mapping here, I'm going to have xy original, and all of this is happening to the horizontal, so that means everything is happening to x, and our y's will have nothing happen to it. So we have our 1/2 x here. Going to the left means we're going to go -3 to it, comma y, and there we go. That's going to be my new mapping. In this next set here, it says given the coordinates for f of x, state the new coordinates for g of x. And this is just a continuation of the previous two examples above. So, and again, just a quick reminder, the mapping on them was the following. So the first one here, we're going to go 1/3 x, comma 2y. And on this half here, sorry, that's a bracket. And on this half here, we have our 1/2 x minus 3 comma y. Okay, here we go. Plugging our x and y values right into here for the mapping 0 and 0, go into here, we end up at 0, 0. 3, 3, we're going to plug in individually, so this 3 goes in here, so 1/3 times 3 gets me to 1, and 3 times 2 gets me to 6. 9 times a third gets me 3, and 2 times 2 gets me to 4. On this side here, I'm going to plug in 0, 0 into this equation. So if I had 0 here, so that's 1/2 times 0, which is 0, minus 3 is now -3 overall for x. 0 times y is, when we sub in, is just going to be 0 there. 3 times 1/2 gets me 3/2 minus 3. So I'm going to quickly use a calculator to figure that out. So basically 3/2 minus 3 should get me to -3/2. And 3 for y here because my y value doesn't change. I'm going to quickly default in the 2 for my y value here because again that doesn't change. This 9 times 1/2 uh, is 4.5, and then 4.5 minus 3 is 1.5, and the way I'm going to write 1.5 is 3/2. Done. In this next example here, in example 2, it says given the function, again we're working with a quadratic function, graph the transformed. So we're doing this -2 f of x plus 1 to our original x squared. So first off, I'm going to start off by graphing my original quadratic. There we go. We have my original quadratic done. Before I start figuring out my next graph, I'm going to rip apart this equation just to see what I have. I have a negative there, so I'm going to write down a few quick notes here. That negative in front of our function means we have a reflection. And that means it's a reflection on, well, which axis is it? Is it going to be your x or y? It's going to be a reflection on your x-axis. That takes care of the negative. The 2 in front of our function means we have a vertical stretch. So we have a vertical stretch by a factor of 2. And that plus 1, again, that's a vertical translation. We have a vertical translation. If it's positive 1, that means vertical translation 1 unit up. In terms of mapping, let's go straight to our mapping here. We have a reflection on x, so that does not affect x. We have a vertical stretch, which does not affect x, and we have a vertical translation, which doesn't affect x. So here, x is just going to stay as x. On our y value, we have negative for a reflection, 2 for the vertical stretch, y, and then we're going to go 1 unit up, so that's going to be plus 1. So here is my new mapping. It's minus 2y, and that's a y there, plus 1. If I take all of my coordinates here and I sub in values, I'm going to see what I get. So if I subbed in 0, 0, x would be 0, y would be positive 1 overall. If I subbed in 1, 1, x would still be 1, y would be negative 2 plus 1, which is at negative 1. At negative 1, positive 1, so at negative 1, x here stays the same, positive 1, we're going to end up with the same result as before, and of course, because it's a parabolic function, it should have mirrored and matched up. And finally, at 2, 4, 2 is going to stay here for x, but we got to figure out what happens to that 4 for y. Well, if you had 4 here, that's negative 2 times 4, which is negative 8. Plus 1 makes it negative 7, and I don't believe I have enough squares. 1, 2, 3, 4, 5, 6, 7 is somewhere here off the grid. I'm going to try my best to match it up. 7 should be there. And now I connect my dots. There we go. That's example 2. In example 3, we're switching gears. We're going to work with absolute value graphs now. So very first thing I do, I'm going to jot down an absolute value graph. And again, I only need about 5 coordinates here, and that's usually good enough for my graph. There we go. That's my original f of x equals absolute value of x. And so I'm going to quickly label that as well. So this is my f of x equals absolute value of x. So what's happening to this absolute value? Well, we're going to do a few different transformations here. We see a negative, we see this half. So that means that there's a reflection, there's a vertical stretch. I see this 2x minus 8. Again, I don't have a dedicated b value. So that means I probably need to factor before I attempt that. And then I have this plus 1 at the end here. So the very first thing I'm going to do, I need to factor this equation. So g of x is going to equal the following, negative 1 half f bracket, and now if I factor out this 2, I have 2 times x. 2 times x gets me back to 2x, and 2 times something gets me back to negative 8. That something had to be negative 4. Then I'm going to double close my brackets, plus 1 on the outside. So let's break down this equation here and see how many transformations we have. Well, first off, I see that negative, so that means we have a reflection. So here we have a reflection. And again, that negative is on the outside, so a reflection on the x-axis. Again, the pattern that we want to do this in is RST, so I'm going to search for any other reflections here. I don't see a negative on my b value, so there's no other reflections. S is our stretches, so I'm going to go in order left to right here. So the very first one I see is that 1 half, so that means I have a vertical stretch by a factor of 1 half. Notice that there's no negative here because, again, we dealt with that negative in the reflection. I see a 2 here, so that's a horizontal stretch. And this is going to be by a factor of 1 half as well. So a reminder that once you have a b value, when you pull it out into mapping over here, or when you pull it out into your descriptor, you still need to reciprocate it. You still need to reciprocate it. Here we have this minus 4, so that's a horizontal translation. And we have minus 4, meaning that we're going to horizontally translate it 4 units to the right. And last but not least, we have this positive 1, so that's a vertical translation. That means we're going to go 1 unit up. So in terms of mapping, what do we have? So in terms of mapping, let's jot down everything that we have here. So really quickly, this one, reflection, vertical stretch, vertical translation, all affect our y value. I only have these two, horizontal stretch and horizontal translation, that only affects our x value. So in terms of mapping, I have 1/2 x, 4 to the right is plus 4, comma, negative 1/2 y plus 1. I'm going to try my best to squeeze it in there. So there's my new mapping equation. So again, pick some coordinates and let's see what we get in terms of mapping. So let's pick 0, 0. So if you had 0, 0 here, you'd end up with 4, 1. 4, 1 is where my new vertex is going to be. So 1, 2, 3, 4. 4 and 1 is right here. The question is, which way are we going with this graph? Let's pick another 2 points. So let's pick 1, 1 to see where we're going. So if you picked 1, 1, we're going to end up with a half and 4, so that's 4.5. So that's kind of ugly. So 4.5 is going to be around here. So I probably don't want to pick 1, 1. Let's pick the next available number. Let's go with 2, 2, so that we don't have to deal with any decimals. At 2, 2, this gets you 1 plus 4, which is 5 for an x value, and that's going to be negative 1 plus 1 for a y value. So we're going to be at 0 if we chose 2, 2. If you chose negative 1, 1, again, you'd end up with fractions. I don't want to deal with the fraction. It'd be around here, around 3.5. Let's pick negative 2, 2. If you picked negative 2 here, that's going to be negative 1. Negative 1 plus 4 is 3, so we're right here. And negative 2, so 2 negatives make a positive, so that's, where are we? No, sorry, that's a positive. So again, that'd be negative 1 plus 1, so that we're at 0. So here's my graph. And I have enough dots here that I know that it's going to follow this pattern here. So I'm just going to build my graph. I have a line going down. Too far. And another one going this direction here. There we go. Let's state domain and range for both of these functions, and it's asking you for individual domain and ranges. So here we go. On the original, our domain, and I'm going to use set notation, by the way, our domain x such that x is an element of a real, because we're going to negative infinity to positive infinity. My range for this one, the lowest I'm going was 0, so I'm going to go 0. Y has to be greater than or equal to 0, but yet y has to be an element of a real as well. So that's the first one in set notation. Let's switch it up and let's do interval notation for the next one, just because we can. So domain and range in terms of interval notation. So domain on our red graph, more or less on our g of x here, we're going to negative infinity to positive infinity. So rounded brackets whenever you deal with infinity. The lowest we're going to go in this case here is negative infinity. The highest we're going up to is positive 1 there. And because we want to include 1 in our answer, I'm going to put a square bracket there to finish this off. And that was example 3. In example 4 here, we're trying to figure out the following. So we have two graphs. We have g of x and we have f of x. And you want to determine the equation of g of x in the form a f of b of x minus h plus k. So you want to write it in terms of f. Okay, so we don't actually truly know what the function is. So what do we do in this example here? So we basically need to compare a few different things. The very first one I'm going to compare is where my vertex is, where my initial versus my final vertex. So I'm going to write that off to the side here. Vertex. So on f of x, we are at 0, 0 for a vertex. On g of x, where's our new vertex? Our new vertex is going to be at -7, +2, it looks like. So in terms of my vertex, if I am moving these dots, there's definitely some sort of translation going on here. So we got, for our x's, we're going 7 to the left. So we have a horizontal translation, 7 units left. And we have a vertical translation because we went from 0 to 2. So that's a vertical translation, 2 units up. And basically that sums up our horizontal and vertical translation. So we got that down, at least for now. Next up, you want to look at is any 2 points that you can kind of compare to be the same. So I'm going to look at endpoints, okay? And in fact, I'm going to circle 2 endpoints that I'm going to compare. I'm going to look at this guy here, which is 4, 4. And I'm going to compare it to this guy here, which is at -6, 10. So what's happening? So I'm going to look at it in terms of from my endpoint to that vertex, because that's where I started. So I have a vertex here to that endpoint, and I have a vertex here to this endpoint. Okay, so that's what I'm comparing. Basically here we can say something along the lines of, if I had so if I have this endpoint over here at my vertex of 0, 0 to 4, 4, and I'm just going to quickly jot down a few notes here. If I went from 0, 0 to a distance of 4, 4, that doesn't look anything weird at all, so I'm just going to leave that as a fact for now. Hold on, I'm going to move down, or I'm going to take a look at this guy here, and I'm going to compare it over here. So basically, how do I word it? If I recount this vertex here on my g of x as 0, 0, I am not stretching it out for 4. Does that make sense? I'm not going all the way out from here to about 4, which would have been over here. I don't have that stretch. I'm going from here straight to right here. So definitely there's some sort of compression horizontally happening. The question is by how much? So in comparison, we have the following, and sorry, I lost my circle there. And I'm just going to jot down some of these coordinates here. So this here is -7, 2, and we're going to compare that to -6, 10. So it's basically you're comparing your endpoint and vertex. So from here for x to this x here, that's a distance of 4, whereas from here -7 to -6, that's a distance of 1. The question is, how would you change your distance from 4 down to a 1 horizontally? Well, that means I must have had a horizontal stretch somehow. To go from 4 to 1, that's a horizontal stretch by, if anyone wants to guess, by a factor of 1/4 or by a quarter. Okay, so that's not too bad. That's okay. The next one I'm going to compare is my y values. So again, my y values, I'm going to start at the vertex and I'm going up to that coordinate there. So this is almost a distance of 4 away here. So we got, wrong color. So my y values here is a distance of about 4. But then I'm going to compare it on my new graph here. My new graph here, I'm going from 2 to 10 here, 2 to 10. So that's a distance of about 8 away. Okay, 8 away. So the question here is, if I had a distance of 4 originally, but then all of a sudden in my g of x I have a distance of 8 away from my y's, how far or how much of a stretch is that? So this here is a vertical stretch by a factor of, well, to go from 4 to 8, that's a factor of 2. So I'm going to try to put all this together. So this fact here, horizontal translation, horizontal stretch, vertical stretch. We're going to put all these facts into our equation that we had originally at the top here. Okay, so here we go. And I'm just going to carve out some space here. So we got y equals, and my very first one, A is my vertical stretch. So I have a vertical stretch of, and let's choose a different color. Let's choose, so I have a vertical stretch by a factor of 2. And then I would have had f bracket, and now I need a b value here. Well, if I have a horizontal stretch by 1/4, my b value should just be 4. And then I'm going to have my bracket and then my x here. And beside x, I need my horizontal translation. It's going to be 7 units to the left. So that's really plus 7. That needs to go beside x there to move it 7 to the left. I'm going to double close this off. And then I got to figure out my vertical translation, which is 2 up. So it's going to be plus 2 at the end to cap that off. So there we go. That's going to be our new equation. We got y equals 2f of bracket 4 bracket x plus 7 double close plus 2 for a final answer. In example 5 here, what do we have here? So in example 5, you have f of x up top, g of x on the bottom, and it says here, graph the function y equals g of x represents the transformation of the graph y equals f of x. Determine g of x. So we got to figure out, well, what is this new equation down here to get us to a curve that looks like this? Again, the very first thing I want to do is compare my vertex. I want to compare my vertex. So again, my original vertex on f of x versus my vertex on g of x. So my vertex on f of x was at 0, 0. My vertex on g of x, well, where are we? We are at 3, and it looks like -4. So that's 3 comma -4 for a vertex. So again, right away, right off the bat, we have the following facts. So from 0 to 3, that's a horizontal translation. And it went from 0 to 3, 3 positive. So that's a horizontal translation, 3 units right. Next, we went from 0 to -4 for our y value. So that's a vertical translation. That's 4 units down. Up next, we got to figure out, well, did we have any stretches occurring? So let's compare some dots on the original versus the new. So on the original, I have my vertex right there at 0, 0. At 1, there should be a dot at 1, and at 2, there should have been a dot at 4 there, because this is a standard parabola. And there we go. I'm just filling in a few dots there. At -1, it should have been at 1, by the way. On our new curve, we have our vertex here. This is technically their version of 1, 1, which is 4, 4, and technically, what is that? -5 and 2, -5 there. Kind of hard to read, but we're going to try our best. And the next one should have been at 5, and it looks to be 8 versus 1 and 8 there. So in terms of stretching, these dots here are the exact same dots as these ones down here. So in terms of stretching, there is no stretching. So I'm going to jot down a quick note, no stretches. And again, how do I know that there's no stretches? My shapes are congruent. They are the exact same shape. My coordinates have changed. Yes, the numbers have physically changed, but the distances from the vertex have not changed at all. It's still a distance of 1, 1 and a distance of 2, 4. 1, 1, 2, 4 away. So there's no stretches at all. I definitely have a reflection happening here. So if I had a parabola facing up, but then suddenly I have a parabola facing down, I definitely needed to reflect it over the x-axis. So I'm going to quickly jot down reflection on x-axis. So basically with this, we have enough information to plug it into our equation. So here we go. We have y equals again, let's start off with my reflection on x-axis. So if I reflection on x-axis, that's going to be negative outside of the function. no stretches, so I'm going to leave that as just a negative, no number next to it at all. I have f bracket x. I have a horizontal translation, 3 units to the right, so that's going to be minus 3. Close that bracket. And I have a vertical translation, 4 units down, so that's going to be minus 4 outside of our function. And there we go. That's our new equation. And instead of y equals, I know that this is truly just g of x, so I can rewrite this as just g of x equals negative f of x minus 3 minus 4. There we go. And that's what we were looking for, because it says the graph of the function y equals g of x represents blah, blah, blah. Determine the equation of g of x. So we have this new equation for g of x right here. In example 6, what do we have here? So in example 6, there's no picture. There's nothing here to do. All we have to do is write the equation of the transformed function g of x. So we got to go through our question and jot down a few key points. Vertical, so it says stretched vertically by a factor of 2, so that's vertical stretch by 2. We have a reflected in the y-axis, so that means it's a horizontal reflection. We have translated 3 units to the left, so if we're translating 3 to the left, that means we have a horizontal translation, 3 left. And translated 4 units down, so that's a vertical translation because we're moving it up or down. We're moving it down, so we got 4 down. There we go. Write the equation. So here we go. Let's write down our equation. So we know the function is x squared for a function. So here we go. So reflection, horizontal reflection, that's going to be inside our function. So on the outside, there's no negative on the outside. We do have a vertical stretch, so that's a 2 on the outside of my function. Brackets, here we go. And then we have negative, wrong color. We're going to put a negative here inside the bracket, and this negative is going to represent that horizontal reflection. Negative bracket x goes here, and where are we going? We are going 3 to the left, so that's going to be plus 3 right here, because that's going to be the opposite once we pull it out. 3 to the left, double bracket to close that off, and minus 4 on the outside here for that vertical translation of 4 units down. And again, this is going to be our equation. The only thing I am missing right now is my function. And so my function, I'm just going to quickly squeeze it in. Should have gone right here. I'm going to squeeze in my squared. It's a squared function. So there we go. Squeezing that in. And reapplying that bracket. There we go. So we have this function, and this 2 and negative 4 are outside the function. Here's my function, and we are done. In example 7, it says given f of x equals this absolute value of x squared minus 4, graph the transformed function g of x that happens to this graph here. So first off, we got to start graphing whatever this x squared minus 4 graph is. We got to figure out what that is. So x squared minus 4 is, well, first off, x squared is a parabola minus 4 means I moved it 4 down. But within absolute values, that means I have nothing below my x-axis there. Everything's going to be positive. So my very first dot is going to be right here at 0, 4. My next ones here are at 1, 3, negative 1, 3, 2, 0. And I'm going to have another dot here. 3 is going to be at about 3 and 5. Negative 3, 5. So basically what's going to happen is we are going to have this W kind of looking graph. So we have a part of a parabola going down, part of this parabola coming down here. And this one here is kind of one of the weirder graphs to do because we have a quadratic within absolute value. So it's going to look something like this. And I apologize, this line should have been a bit more curved in something like that there. So from this is going to be my original graph here. From this graph here, I want to do the following transformation to it. I want to do this 2x plus 4 plus 3 to it. Well, first off here, I don't have a dedicated b value, so I want to rewrite and isolate this equation. So I'm going to rewrite this equation, g of x equals f bracket 2 bracket x. So we got 2 times x gets me back to 2x, and 2 times what gets me back to 4. It's going to be plus 2, close, close, plus 3 on the outside, and there we go. So what are we doing from our f of x to our g of x? Well, we have a horizontal stretch here. So let's jot down a few notes here. So we have a horizontal stretch by a factor of 1/2 once you pull that out of the equation. We have a horizontal translation, and that positive 2 means we're going 2 to 2 units left. And that positive 3 is a vertical translation. So we're going vertical translation 3 units up. So from here, what do? We could fill in our equation for mapping. So that's what I'm going to do. It's easiest to map this out. So we have x comma y original, which is going to be all these dots here. So we have about 7 dots here that we might want to play around with or graph. And what are we doing to them? So in my new bracket, in my new one, I have 1/2 x because that's the horizontal stretch. So we have 1/2 x here. And because we're going 2 to the left, it's going to be minus 2. My y value, I'm not multiplying it by anything, but I am going to move it up 3. So it's going to be plus 3 there. So here is my new mapping equation. So all I do is take most all of these coordinates here, plug it into this mapping, and see what we get. So the first one I'm going to plug in, of course, is my vertex. So I'm going to always double check my vertex. So 0, 4, I'm just going to do a few of these off to the side here just so that you see what's going to happen to these coordinates. So if I had 0, comma 4 originally, so here 0 times a half is still 0, minus 2, I'm at negative 2. 4 and 3 make 7. So this is going to be one of the coordinates that I have. It's going to be at negative 2. So that's 1, 2, and positive 7, which is technically kind of off the grid, but you're going to try your best here. So we got 1, 2, 1, 2, 3, 4, 5, 6 should be here. 7, probably yay high off the grid there. Um, the next two coordinates here. So let's check this one here. So let's use 1, 3. Let's check 1, comma 3. Let's see what happens to this guy here. So on this one here, if you had 1, this is going to get me a fraction. So we got 1 times a half is 1/2. 1/2 minus 2 is going to get me, oh boy, negative 1/2, which is negative 3/2. And 3 plus 3 here is going to get me to 6. So somewhere in the ballpark of 1/2, negative 1/2, I'm all the way up at 6. So it's going to be, so this was 5 here, so 6 should be right around here. And it should have mirrored it on that side too. Let's choose this coordinate here. That's going to be my next one. So this is at 2, 0. So what's happening at 2, 0? So our new coordinate at 2, 0. So 2 times a half is 1. So we got 1 minus 2, which is just negative 1. 0 here, 0 plus 3 is going to just be at 3. So I'm at negative 1, 3. So at negative 1, I'm at 1, 2, 3. So I double up around here. That means over here, I'm going to have a coordinate right here as well. These last two are going to be off the grid, but just to show you that they're going to be off the grid, we're going to test. So that's 3, 5. And I'm definitely going to get the ugly fraction here. So this is going to be half times 3, which is 1/2 minus 2. So that we're at negative a half there. And if you want to try your best to graph negative half, again, you can. So this is negative half. And 5 here and 3 make 8. So we are well off the grid here. So that one is going to be just slightly above this guy here, it's going to probably be somewhere in that letter G. So I'm going to try my best to graph and connect these dots here. So that's going down here. Then from here, at these coordinates here, we're going to shoot straight up. And I'm shooting way too far to the right there. Around 1/2 looks like it's up there. I'm going to connect that down, and around 1/2, 8. I'm going to try my best to connect that down. So it looks like that there. So this one here, kind of slightly ugly in terms of pictures. If you did this on a graphing calculator, that is, it's going to look a bit nicer, but yeah, that's kind of what we have here. Last but not least, I had an example 8 somewhere. All right, sorry about that. Here we go, found my example number 8. So in example 8, we got write the equation and describe the transformations performed of the function y equals f of x if x is replaced with 2x. So we're going to do this in little sections here. So let's rewrite that. So if you had y equals f of x, the very first thing they want us to do is replace x with 2x. So well, what's that going to get us? That's going to get us y equals f of 2x. Sure. Then y is replaced with 4y. Okay, so my next line is going to say 4y equals f of 2x there. Then after that, what are we doing? Then it says then x is replaced with x minus 4. Sure, why not? So we got 4, sorry, that's a horrible looking 4y equals f bracket 2. And instead of x now, I'm going to throw on a bracket here, x minus 4. Double bracket to close. And then finally it says here y is replaced with y plus 6. Okay, so we have 4 bracket y plus 6 bracket equals f 2x minus 4. There we go. That's our equation that we're trying to figure out. This here we kind of don't really work with. This doesn't really make much sense to us. So the very first thing I want to do is isolate for this variable y. I want to get y by itself there. So I'm going to move this 4 to the other side first off. So I'm going to divide by 4. That means I have y plus 6. So I can drop brackets now equals 1/4 f of 2x minus 4. So again, I divided by 4, which is the same thing as multiplying by 1/4, by the way. Up next, I want to get rid of this 6. I'm going to move it to the other side. So here I got y equals 1/4 f of 2x minus 4 goes here. Close bracket again. Minus 6 at the end there. There we go. We are done. And that is our equation. And it says write the equation and describe. So now we just got to jot down all the transformations that have occurred in this graph. So what do we have? No reflections. First off, double checking both my A value and B value. No negative signs on them, so no reflection. So I don't have to mention that at all. So right here, I do have that 1/4. So that's starting off with a vertical stretch by a factor of 1/4. I have a horizontal stretch because that's my dedicated B value. It's a horizontal stretch by a factor of, instead of 2, because that's 2 is in my equation, it's going to be 1/2 as my descriptor. I have a horizontal translation because that's what that minus 4 is. So minus 4 means I have horizontal translation 4 units to the right. And last but not least, I have a vertical translation because that's what that minus 6 is. So VT here for vertical translation, we're going 6 units down. There we go. And there we go, folks. That is lesson 3 in a nutshell. And if you have questions, please feel free to ask.